Welcome to a new video. In this video we will discuss another circuit of voltage to current converter. We will see how we can use this circuit. We're using the op-amps to create a load current which is affected only by one circuit parameter. Of course we will see that step by step in our calculations and we'll verify these in SPICE simulations. Okay, the objective is we have this circuit given which is a voltage to current converter. We have two op-amps which are in this case considered to be ideal, and we have two resistors. We have a load resistor RL and we have our setting resistors R. And there is in this case one voltage source input which is Vs, but you can also have one voltage source at this node, another one at that node, so it doesn't have to be with single voltage source at the input. Now again we would like to determine the expression for our load current, which is actually shown here, in terms of this input voltage Vs or source voltage Vs. So how do we do that? Now, first the calculations, of course, and then we will see what we have done and verify this in SPICE simulations. And before we move on, let's use the op-amp ideal characteristics. So in an ideal op-amp, you have no current inside, so this is 0. This current is 0. The current here is also 0 in the non-inverting input, and also in this non-inverting input is all 0. So in the two input terminals of these two op-amps, OP1 and OP2, we have no current. Okay, then we can say this current IL is equal to this current, which is 0, plus this current. Now that means IL will be IR. So we will see that this resistor current is equal to the load current. That can be used later in our analysis. Now, before we work out the calculation, it's also handy to designate the nodes. I designate here the node X, another node here is Y. Okay, now the Vx is equal to Vs, this node voltage. Why? Because we have negative feedback in this OP1, and due to the negative feedback, the op-amp tries to make this node voltage equal to that node voltage. Now, since this is Vs, which is already set, then this should be also Vs. That is actually this condition. Now looking at Vy, it should be 0. Why? Because the OP1 is also negative feedback in the negative feedback configuration. Since this input is 0, it's just grounded, then this should be also, this node voltage will be also 0. That's actually shown here. Okay, now we also know that the IL must be IR, just discussed, because the current in the OP1 in an inverting input is 0. And no current flow, of course, in any other input terminal. So there will be current flowing out, but no current in. Now, using these conditions, we can now write the following. We can already say that the resistor current, IR, will be the voltage Vx minus the voltage Vi over the resistor itself. That's just Ohm's law, of course, but we know that Vx and Vy is, that is then Vs minus 0 over R. Now in this case we have then IR is equal to Vs over R. Now since IR is equal to IL, we can say load current is equal to the input voltage over the resistor R. So this resistor here will set the load current which is flowing through this load resistor, and this load resistor is not in this equation, so it is not affecting the load current in this case. That's interesting. We will check that shortly. Okay, let's now go to the simulation results to see that this is indeed the correct expression for our load current in terms of the source voltage. Okay, now this is the circuit we will use. We have now here the resistor value for the load is 2 kilo ohm and 1 kilo ohm for our setting resistor R. Now, when you look at now this graph, which is a pure sine wave for the input, which is a 10 volt peak, so peak 20 volts, and we have here 100 hertz frequency. So we have here Vs, which is then nicely a sine wave, and our output load current, IL, is also a nicely sine wave current. Now we have our resistor load is 2 kilo ohm, but our resistor setting resistor is 1 kilo ohm. Now we see here from this equation that should be then the maximum value is 10. For example, if I pick the maximum value for our input voltage, divided by the 1000, which is our resistor here, will be then here in this case 10 milliamps, which is then correct. Now if I go down with my input voltage to minus 10 volts, I also have minus 10 milliamps. So it is just following exactly, it is not inverted, so doing exactly this formula. So this is indeed correct. So it is not affected by the load resistor, but we need to check that carefully. It is really the case that this load resistor do not affect the value here. Okay, let's do that now. Let's see that the effect of the load resistor on this equation is 0 in this ideal situation. Now I will now set the setting resistor R to 1 kilo ohm. That means I have some specific current I want according to this equation, the load current, and I will now change my RL and see that the effect is no, there is no effect on the load current. Now these are the results. Again, the blue line, the blue graph is our input voltage, still the same, 10 volts peak, so 20 volts peak, and 100 hertz as the frequency. Let's go from top to bottom. You see here this brown color, which is for the load resistor of 100 ohms. What you see is peak, or the peak value is 10 milliamps, and also the minus 10 milliamps for the minimum. But if I go up with a load resistor to 200 ohms, it doesn't change, still the same. And this for 500 ohm for the load resistor, it is still 10 milliohms peak and minus 10 milliohms the minimum value, milliamps, so 10 milliamps and minus 10 milliamps. So the same also for 1 kilo ohm, same for 2 kilo ohm. So it doesn't change at all. No, actually nothing is changing here. So we can say for this setting, for the resistor, and the changing value of our load resistor, the load current is not changing. So the load resistor does not affect the load current, and this is according to our formula we have found in the previous discussion. Now let's also do the effect of the setting resistor R. That will definitely affect the load current, because that is what we also say in our expression. Now we keep our load resistor here as 2 kilo ohms, and we will now change this setting resistor R. Here are the results. So we have now here the load resistor 2 kilo ohm, that's set. And now we are changing. Now we go from 100 to 200, etc., all the way to 2 kilo ohm for the resistor R. Now you can see from this equation that if this R is increasing, then the load current must decrease. It is actually what you see here. Again, the Vs, which is our input voltage, will be 10 volts peak or 20 volts peak with a frequency of 1 hertz. So you can see that for yourself for different values, and then also check that using this SPICE simulator, that the effect of this R is that it is only decreasing the current or increasing the current depending on the value, but the load resistor will not affect this load current, which is actually a nice situation. Why? Because if you have an element here, you want to supply the current for it, or you want to heat up something with a heater element, then you can say this change will not have an effect on the current provided here in this branch. So we say, again, the resistor R will have an effect on the load current according to this formula, but the load resistor will not affect the load current. So this is indeed verified and correct as we have calculated. Alright, what's our example considering the voltage to current converter circuit? In this case we have calculated the required formula to go to the load current from the input voltage, and we have seen that the load resistor is not affecting our load current. If you have any questions, comments, please let me know. I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation, and see you next time in another video.